Swayam Prabha. Digital India. Educated India.
Okay, so the other thing that I want to briefly talk about is that this whole idea of probabilistic modeling of data can be thought of as basically doing probability density estimation. Okay. And it's again not surprising because if we think of the whole pipeline of probabilistic modeling, all we are doing is basically playing with distributions or manipulating distributions or estimating distributions, because if you think of the likelihood distribution, this is basically nothing but a probability density, right? So if you have continuous variables, then it's p of x given mu, the likelihood is a density, prior distribution is a density, posterior is a density, plug-in predictive, posterior predictive, they all are probability densities, right? They can be continuous or discrete depending on the type of variables, data, or the parameters you have, right? And in all these problems, typically you have to, in some cases, you have to estimate this likelihood distribution, because if you're trying to estimate mu, you are estimating a density over mu, right? So which is why I'm just saying that you can think of in very broad terms, you can think of any probabilistic modeling problem as basically doing density estimation, okay? So the density estimation is typically of the parameters that you're trying to learn as a function of data, or it could be estimating density of some future data, right? The test data given the past data, okay? So in all these cases, you are doing some sort of density estimation, okay? Okay. Even in supervised learning problems, right? So that we have, so our setting right now of estimating the mean of a Gaussian distribution is an unsupervised learning problem. You're given a bunch of observations and you're just trying to learn the mean of the Gaussian, of the Gaussian, underlying Gaussian distribution. But if you have a supervised learning problem, which you might have seen in the previous lectures, where you're trying to predict some value y given some x, so in those cases also, you are again learning, probability densities, because there the data is in form of x, y, x and yn, x1, where you may have n observations. But again, the goal is to estimate something like what is the probability of of the output of a new input x star. So p of y star given x star. This is again a probability density, right? And again, this is like a prediction in a supervised learning setting, right? So what is p of y given x? And in fact, we will look at it in more detail in lecture 2. But even in this problem can be solved in two ways. Are you going to use a single value of the weight vector, or all possible values of the weight vector? So are you going to compute a plug-in predictive of this form, or a posterior predictive, right? Where you average over all possible weight vectors weighted by their posterior probabilities. And that's something that we'll look at in lecture 2. Okay. Okay, so let's summarize what we have done so far. So as we have seen so far, we can model both. In probabilistic modeling, we can model both the data as well as parameters using probability distributions, right? So it's basically, it's a thing of, you have to basically do a lot of probabilistic, you need some dexterity to deal with probabilistic modeling, right? So if you're comfortable manipulating probability distributions, if you know the properties of probability distribution, then you can do a lot of things with probabilistic approaches. And as I say, again, I'll just like to repeat that both data as well as parameters, right? They both can be modeled using probability distributions. Because data, you need a likelihood model, p of x given the parameters. For the parameters, you need a prior distribution, p of theta or p of mu. And the posterior distribution is also a probability distribution. One good thing about using probability distributions is that, again, I'm just summarizing, that we can incorporate prior knowledge, right? Now, one thing that I did not specify earlier is that I only talked about prior information about, or prior knowledge about the parameters, right? But you can also have some prior knowledge about the data itself, right? So you may have some sense as to the data comes from this particular distribution. I have some knowledge of what the distribution is, right? So why choose Gaussian? Why not some other distribution, right? So if you have some information about what sort of distribution might have generated the data, you can choose that likelihood model, right? So which is why it's very natural in probabilistic models to inject prior knowledge using these probability distributions. So you can choose a suitable likelihood model, suitable prior distribution if you have some prior knowledge about the problem. Okay. So yes, you can choose a suitable likelihood model, p of x given the parameters. You can choose a suitable prior distribution, p of mu, or p of the parameters in general. We have also seen that we can infer the full posterior distribution over the parameters, p of mu given x, okay? Which has many benefits. First of all, as we saw, that the posterior tells us about the certainty or uncertainty about the parameters, which usually reduces as we see more and more data, okay? And the other nice thing about using a full posterior distribution is that we can average our predictions over all possibilities of the parameters. So this example, that this picture that I have here is for a classification problem. So suppose I'm trying to learn a classifier for separating data from two classes. So typically in a non-probabilistic model, we learn a single hyperplane that separates the two classes, right? But as we will see later on, if we take a probabilistic approach, we can learn a full distribution over hyperplanes, right? So rather than trusting a single hyperplane, we can actually get a full distribution over all possible hyperplanes, right? And we can average our predictions using all these basically hyperplane predictions. So we can actually get a posterior weighted average prediction. Okay. Okay. And that is one of the key ideas in what is known as Bayesian machine learning. So probabilistic modeling is any modeling approach where we are treating modeling data and parameters using probability distributions. But Bayesian learning is the specific type of probabilistic modeling setting where we learn the full distribution. So if we are going for the full posterior distribution over the parameters, and if we are using the full posterior distribution to get these posterior weighted averaged predictions, then we say that we are essentially doing Bayesian learning. Okay. So not all of probabilistic modeling is Bayesian modeling. Bayesian modeling is specifically when we are going after the full posterior distribution over the parameters and using the full posterior distribution to average over all the over the entire posterior distribution. Okay. Again, any other questions before we move on? Okay. So in the rest of this lecture, let me briefly talk about some of the other benefits. We already seen some of the benefits that we can incorporate prior knowledge about the data and the parameters. We can learn the full posterior distribution over the parameters. We can do averaged predictions rather than relying on a single point prediction. So let's look at some of the other benefits of probabilistic modeling. So one very appealing and natural benefit of probabilistic modeling is that you can think of it as a continuous or online process, okay? Especially the Bayesian inference pipeline, because you typically start with a prior distribution, right? And then you get some data, right? And then you apply the Bayes rule and you get a posterior distribution, right? Now, the posterior distribution can also be treated as a new prior if you get some new data, right? Because you started with some belief about the parameters, you got some data, your belief got updated into the posterior distribution, right? Now, that is your new belief about what your parameters look like, okay? If I get a fresh batch of data, my current posterior can now become the new prior distribution, okay? And I can provide more data, and then my belief can be further updated, right? So it's kind of a cycle, right? Basically, so as we see more and more data, our posterior becomes more and more refined. Okay, so which is why I'm saying that it's kind of an online procedure where and that's how humans also learn. Sometimes we start with some initial hypothesis that about some phenomena, and then we observe something from that phenomena. Our beliefs get updated, and we continuously observe, and our beliefs keep getting updated and updated. So the same kind of a formalism or paradigm applies to the Bayesian inference or probabilistic modeling in general. Okay. So this picture that I have on the right-hand side is basically showing that when you start with, let's say, n equal to 0 observation, then you have kind of a very flat or very broad kind of a belief, right? But as you see more and more observation, your belief becomes narrower. You become more and more certain about the thing that you're trying to learn. So this picture kind of encapsulates that thing. Okay. The other benefit, that's something that we have already talked about, is that since we are learning a full distribution over the parameters, we are not learning a single solution for our parameters, but multiple solutions, right? So, and that naturally gives us the uncertainty. So the idea is that so in this picture, as you can see, suppose I have these 5 dots, and we are trying to fit a regression model, okay? Regression you all have seen. I guess linear regression you have seen. But suppose we can fit a non-linear regression model on this, right? But of course, with just 5 observations, it's not clear which of these curves is the best fit, right? But that's the good thing about Bayesian modeling, because it says that, well, let's not trust a single fit. Let's use all these fits and weigh them differently, right? So if in this problem, if I'm learning all these different curves to fit this data, when I finally make predictions about future data, I can use all these basically like curves to make the predictions, right? And as you can see, if I'm using multiple solutions, then I can get sort of a confidence interval about my predictions, right? And one thing that you can see in this picture, and it should be intuitive also, that as you move away from the data, the uncertainty increases, right? As you are, so because all these curves are kind of passing close to the data, but as you move away from the data, the curves diverge, okay? And it's again kind of intuitive, because if you have like, you will be fairly confident in regions where you have data, right? But if you don't have data, you will have, uncertainty, right? And it's important to encapsulate that in any model, because a good model should have that kind of a property, that it should be more certain, in regions where we have lots of data, and it should become more, rather than being overconfident about places where I don't have data. Why not just report the lack of confidence, or and which is what translates. So if you have uncertainty in your parameters, that translates into the uncertainty in the predictions. This is something that we'll look at in more detail in second lecture, but this is just sort of an overview. So these vertical bars that you are seeing, so this solid black curve is like the mean prediction, okay? And these vertical bars are kind of at each input, how much is the uncertainty in the prediction, okay? So this is the mean prediction, but there's a lot of uncertainty at this point. Okay. And this is also very useful in things like, there's something called active. So suppose I am trying to learn a regression model. Suppose I have these observations. These black dots are my observations, right? But if I have, and using these observations, I can learn a predictive model, right? With some uncertainty estimate as to how much is the uncertainty about, my model's prediction at any input, even the future inputs, right? Now the thing is, if I have the estimate of uncertainty, right, it's very useful to do sequential acquisition of data. So suppose I can add one more input to this, to my model to refine the model, right? Now, I have all this entire range, right, where the inputs can lie. So suppose I say that, well, I have already learned my model using these black points, right? I want to add one more observations to refine my model. Where should I get the observation? Should I get in a region where the model is very confident, or should I get the observation in a region where the model is very little confident? So little confident, because that will add more value to the model. So this is nice, because if I have a model with uncertainty estimate, then I can probe for more useful data points, right, for futures, which is why the whole paradigm of Bayesian machine learning, where we can actually get quantified measures of uncertainty, it's very useful for problems like sequential data acquisition. So this is another benefit of probabilistic modeling. So another benefit of probabilistic modeling is that we can actually define generative models for data. Okay? So what do I mean by generative model? So in many problems, oftentimes we can explain the data. So suppose I have a bunch of observations, like let's say x1 through xn. We can also associate some latent representation or encoding with the observations, right? In many cases, so we observe some data, but we don't observe some other aspect about the data. For example, suppose I am doing data clustering, right? So I observe the data, but I don't get the cluster IDs, right? Right? So the cluster IDs are labels that are hidden from us, right? So they are kind of latent variables, right? So with every x, we have the cluster ID that is hidden from us. So we can actually formulate this problem as a probabilistic model and learn these the hidden variables. Okay? It's also useful in things like representation learning, where with every data point, I have some compact, compressed representation of the data, right? So there are many other applications in unsupervised learning, like mixture models that we will look at briefly today, representation learning, deep generative models, where these generative models are very, very useful. So talking about deep generative models, so there is a recent, basically, like a lot of interest in designing models that can synthesize data. Okay, so you can just, like, let's say, feed in like millions of images to a model, and the model will learn to generate new images from virtually nothing. So you can just, like, so as this pipeline shows, so you can actually have some observed data, right, modeled by a sequence of hidden variables or latent variables, right? And you can learn this model where these latent variables are just random variables. Okay, so what you can do once you have learned this model, you can actually input another random variable, and the model will synthesize a new data point that looks very realistic. It looks very similar to the data that you have used to train the model. Again, this is sort of an advanced topic which we won't go into the details of, but I'm just talking about some of the benefits that if you take a probabilistic approach, you can actually do all these interesting looking things. Yes, so again, using the same principles that we have seen. So you observe, so suppose I give you x1 through xn, n observations, right? You again define a probabilistic model with some prior distribution on these parameters, right? Yeah, again, yeah. So you have to define an appropriate, distribution on all these variables, and you again do maximum likelihood or map estimation or Bayesian inference, right? So again, you have to. We only looked at a very simple Gaussian mean estimation, but all these problems can be. So in all these problems, you have some observations and a bunch of unknowns, right? So you can always formulate this as a parameter estimation problem, okay? Where you estimate the parameters given the observed data, P of unknowns given the observations, okay? And once you have learned the unknowns, you can actually generate new data from there. Okay. Another benefit of probabilistic modeling is to do information sharing across multiple models, okay? And that is again where the notion of prior becomes very, very useful. So suppose I'm trying to learn not from a single, so suppose I'm trying to build, okay, so let's go back to the same Gaussian mean estimation problem. Okay, so the problem that we looked at was that we are given n observations from that we assume to come from some Gaussian distribution, and then we estimated the mean. But now suppose that I'm given several sets of observations, each coming from some Gaussian distribution, okay? And I want to estimate the mean of each set of observations, okay? Now, I can solve this problem in two ways. I can solve this problem independently for each set, or I can solve them together by saying, so if you recall, in each case, we had some parameter. So let's say theta is the mean of the Gaussian distribution for data set 1. Theta 2 is the mean of the Gaussian for data set 2, and so on. What we can do is that we can say that, well, all these parameters, they all share the same prior. Okay? So in the single Gaussian estimation problem, we had a mu on which we assumed a Gaussian distribution. But if we have several mu's to be estimated, we can say that they all share the same prior distribution. Okay? So we can collaboratively solve multiple problems by sharing information. And it's very natural in a probabilistic setting. You just have to add one more prior distribution that ties together all these parameters. Okay? So this notion of building complex models by combining simple models and sharing information by using a prior is also very natural in a probabilistic modeling setting. Okay? And this is also very commonly used in things like transfer learning or multitask learning, where essentially like each problem is a task that you're trying to solve, okay, or learn. And you can just rather than learning each task independently, you can solve them or learn them collaboratively. Another very important piece of is that or benefit is the idea of hyperparameter estimation. Okay, so if you think of any machine learning model, you invariably have one or more hyperparameters, right? And like for example, if you're solving regression problem, you have this ridge regression, the regularization constant, right? So and typically, how do you set the hyperparameters? How do you find the best hyperparameters? Cross-validation, right? But cross-validation is expensive because you have to, set out some held-out data, do k-fold cross-validation, and it's expensive. You have to repeat multiple times to get the best, setting of hyperparameters. However, in a probabilistic model, estimating hyperparameters is kind of more natural, and it can be done without cross-validation. Okay, and how it is done? Well, here is a very brief, pictorial overview. So suppose I have some probabilistic model. So think of it as a probabilistic model, right? So suppose I'm trying to estimate some parameter theta, and which depends on some other hyperparameter alpha. Okay, if you recall the Gaussian mean estimation problem, we had a prior distribution P of mu which had mu0 and sigma 0 squared as our hyperparameters. I told you that they are assumed to be known, okay? But they need not be known. They may be, we may have to estimate those, right? You may do cross-validation or some other thing, but we can actually, but those are so it's kind of hierarchy. You have data on which you have some, which is modeled by a parameter. That parameter depends on some other parameter. So you have a natural hierarchy. X depends on theta, theta depends on a hyperparameter alpha. Right? But it's a natural hierarchy, and what we can do, we can actually directly learn alpha, which is a hyperparameter in this setting, by just solving a inference problem. Okay? So the idea is that what we can do is, so suppose I want to learn alpha from data. So, okay, so my goal is to learn both theta and alpha. I know how to solve for theta. We already have seen assuming alpha is known, we know how to solve for theta. We can do MLE, map, full Bayesian inference, and so on. How do we solve for alpha? Well, one option would be to say that alpha is nothing but argmax. So what is so we did maximum likelihood. We in order to find mu, we did max of P of X given mu. We can do the same thing for alpha. We can say that the optimal alpha, let's say alpha hat, is argmax of log of p of x given alpha. Okay? So the optimal alpha will be the one that maximizes the probability of data as a given alpha. Okay? It's a probabilistic model. So what is the best, the optimal alpha? Well, the one that gives a high probability to data, right? So this is a perfectly valid, way of solving for alpha, right? Because we now have a probabilistic model. However, what is this quantity, p of x given alpha? X does not directly depend on alpha, right? X depends on alpha through theta, right? But using this chain rule and integral, we can write p of x given alpha as p of x given theta times p of theta given alpha and integrate with respect to over all values of the parameter theta. Now, if I can solve this integral, then all I have to do is basically solve this maximization problem with respect to alpha. Okay, so this integral may or may not be easy, but at least it gives us a way to directly solve for alpha without having to do cross validation. Because all we are trying to do is basically learning alpha, right? So we can simply say that, well, one way to solve for alpha is to find alpha that maximizes the probability of x given data. This is also known as marginal likelihood, by the way, right? So if I think of x given theta, this is the likelihood, right? Which we defined. But if we talk about p of x given alpha, this is called a marginal likelihood because you are marginalizing over all values of the parameter alpha in computing p of x given alpha. Okay. So by the way, this is just one way of estimating the hyperparameter where we are maximizing, where we are doing maximum likelihood but of the marginal likelihood. Okay. We compute the marginal likelihood and we maximize it with respect to alpha. You can also do a map estimation. So if you have what you can do, you can actually use a prior distribution over alpha, and you can do a map estimation or even a Bayesian estimation. There are many ways of inferring alpha, the hyperparameter of any model, either using the maximization of marginal likelihood or map estimation or Bayesian inference. Okay, and it becomes possible because we can just treat it as any other. So it's just another unknown in the model, right? So we have some data and a bunch of unknowns. For every unknown, we can perform MLE or map or Bayesian inference. Okay. Yes.
So it is yet another distribution.
Yes. So the thing is, so there are many. So if you don't have any other distribution, if you have to assume another distribution, you have to assume something else about the parameters. So if you want to stop there, what you can do, you can just say that, well, I'll just do maximum likelihood here. Okay. However, as I said, one of the it's both good and bad about probabilistic modeling that you can keep adding layers and you can put more assumptions about alpha, but at some point you have to stop. Okay, so typically what happens is that as you move away from data, further and further away from data, at some point the influence of the hyperparameters is not that much. So at that point you can just stop and you can just do this because if I just want to solve this problem, I don't need any prior distribution on alpha. I can just do the maximization of this quantity. Note that I don't have p of alpha here. There's no p of alpha. This is just the prior. Okay. Note that prior doesn't. So even though I just said prior as p of mu in the previous case, here I'm explicitly saying that p of is representing it as p of theta given alpha, just to emphasize that the prior over theta depends on alpha. Okay. Yeah. Yeah, I'm kind of done for this session. Yeah, so just a couple of other points before I conclude. So another benefit of Bayesian or probabilistic modeling is that we can also do model comparison. Okay, so typically when we are modeling some data, we have several models that we can choose from, right? For instance, even this problem of Gaussian mean estimation. Why decide that it's a Gaussian? It could be any other distribution also, right? It could be, let's say, a Poisson distribution or some other distribution. So we have a bunch of models, right? So which model is the right model? Now, using the Bayesian inference procedure, we can actually compute the probability or posterior probability of every model given data. So we can even, so suppose I have capital M many models where small m indexes which model number I'm looking at. So suppose I have these different models to choose from. Which is the best model? Well, if I can compute this quantity p of m given x for every model, then the best model would be the one that has the largest p of m given x. Okay. What is p of m given x? Again, Bayes rule. It's p of m times p of x given m divided by p of x. Okay. Okay. So in principle, if I can compute these quantities, the left-hand side, I can rank different models. Okay. So how do I compute this P of x given m? So this is again a marginal likelihood. It depends on typically P of x given parameters times P of parameters given models. But, so it's usually a bit complicated to do this, but in principle this is again doable. Again, I'm not talking about it not because it's not possible, but because it's beyond the scope of this lecture. But you can do this in principle. You can actually compute this posterior probability of every model given the data, and then find the best model. Okay, and you can, whichever model has the largest posterior probability, that will be the best model. The final piece that I wanted to talk about is this very appealing idea of non-parametric Bayesian models, where you can learn the right model size. So in the previous case, we said that we have, let's say, 10 models to choose from, and we want to pick the best model, and we will do this posterior probability comparison to find the best model. Another way of selecting the best model is to have models that can grow in complexity as you have more and more data. So I'll give you a very simple example of a data clustering problem. Okay, so suppose you're trying to cluster data, right? You typically assume that there are 10 clusters. Okay, now is 10 the right assumption? What makes me think that there are just 10 clusters, right? So again, you can do cross validation by trying different number of clusters, right? Which is going to be expensive, right? So how about having a model that says that, well, there are potentially infinite many clusters, okay, before we have started the data clustering. But of course, the number of clusters will be dictated by how much data we have. But if we can somehow provide the model an ability to grow the number of clusters as more and more data is seen, right? So if suppose at some point I have seen 10 data that belongs to 10 clusters, but there is a new data point that doesn't look like belonging to any of the 10 clusters, and if I can have a model that has the ability to create a new cluster, right, then it will be a much more flexible model, right? So the idea of non-parametric Bayesian modeling is basically about having models that can grow in size as we see more and more data. And this is very nice in online learning settings where we have streaming data. So this is something, again, which we will not talk about in great detail, but I'll give you an illustration for the clustering problem in lecture 3, very brief. Again, this is, again, a fairly advanced topic, but I just wanted to mention that this capability is there in probabilistic modeling. If you want to have a model that can grow in size as you see more and more data, it's possible by taking So if you just search for non-probabilistic models, you will find some tutorials that explain this topic in more detail. Okay, so I think I'm done with this session. Are there any questions before we break out?